In this lecture, we want to study the simple harmonic motions. Simple harmonic motion is a type of the oscillatory motions. So let's consider this web page. Okay, the simple harmonic motion in the Wikipedia website. So you can see that if we have the spring mass system, so we have the spring connected to a mass, and if we try to pull the mass in one direction, the mass just oscillates. Okay, go back and forth, go back and forth, go back and forth forever. So this is called the simple harmonic motion. One thing about the simple harmonic motion is that the amplitude of this oscillation must be constant. We can compare this simple harmonic motion with a dot here in the circular motions. So if we try to project the motions of the dot, right, on one plane, for example, if we have the plane here, okay, then you can see that the particle will just go back and forth, go back and forth, go back and forth forever. Another structure that we just want to study is the simple pendulum, such that we have a light string, okay, and then we have a bob hanging down here. So now you can see that the bob will just oscillate, right, go back and forth again forever about a point. So that's called the simple harmonic motion as well. The amplitude must be constant. So now what we want to study in these topics, right? So we just want to talk about the spring mass system here, and then we have the horizontal spring mass system. This will be the first one that we just want to know, and then we just want to study the energy of the system, both kinetic and the potential energy. And then we talk about the vertical spring mass system. So we're going to see how different the vertical and the spring mass systems. And then after that, we talk about the pendulum. We have the simple pendulum, as I have shown you already, and we have the physical pendulum. So we're gonna use the rigid body to oscillate about a point. The first topic, the horizontal spring mass system. So let's consider a mass spring. Okay, so let's assume that the mass spring will have the length equal to this length. But the thing is, if we fix one end of the spring to maybe a wall or anything else, then this position of the spring, let's say that it's going to be at the x equal to 0. So that's called the equilibrium positions. Okay, so this will be the original length of the spring, and the one end of the spring here is going to be at the x equal to 0, the equilibrium position of the spring. Now then, if we connect this end of the spring by a block M, okay, by the block M here, with a mass equal to the M, and then the block is placed on the frictionless floor, so we don't have any friction on this floor, and the spring constant, right, just equal to the K as usual. Then if we try to pull the block M to the right hand side, okay, so let's say that the block is at this position. Okay, the block is at this position, so the extension of the spring is equal to the x. And if we release, right, so you can see from the previous website that the block M will just oscillating up, back and forth, back and forth, back and forth, back and forth forever. So now we just want to find equations of the acceleration of the block M. So what should we start? We should start just from the free body diagram of the object, right? Okay, let's just start from the weight, right? We have the weight here, just go into the downward direction, and then because the block M is placed on the floor, it means that we must have the normal rotation force that the floor exerts on the block. So the normal rotation force just going to the upward direction. Okay, so this will be the normal force. Then because the block m, right, it's just moving to the right hand side with the acceleration equal to the a, as shown in the picture here. But now you can see that the spring is connected to the left of the block M. So it means that we must have the resolving force of the spring, right? The resolving force of the spring that try to pull the block M back to its equilibrium position. So this will be the direction of the force, okay, equal to negative k times, oh sorry, just the k and then times the x, okay, the resolving force of the spring. Now let's just write down the Newton's second law of the motions. Okay, from Newton's second law of motion. Okay, so it said that the net force equal to the mass m and then times the acceleration, right? So now let me just define that going to the right hand side is positive, okay, and then go to the left hand side is negative. Okay, considering the vertical components of the force, right, you can see that the normal force and the mg just cancel out, okay. But now if we look at the horizontal components of the force, we have only the kx here, okay, and then the kx will act as the resultant force or the net force, because we have only the kx, I mean for the horizontal. Then go to the right to be the positive and to the left to be negative. The kx just go to the left, it must be negative. Then we have that negative of the kx, right, is going to be equal to the m and then times the a. Let me just write down the expression in the terms of the d square x by dt square here, okay. So then finally, if you just rearrange equation by moving this to the right hand side and then divide out the equation by the m, okay, so you will get that the d square x by dt square plus, okay, it must be plus k over m times the x equal to the 0. So this is what we get, right? Okay, now we just want to find the solution, I mean the x as function of the terms of these equations. So we have the technique, I mean to solve this is called the second order differential equations, okay. We have the technique to solve this second order differential equation. So we need to guess, okay, we need to guess what? We need to guess that the xt, okay, equal to the a times the psi and then omega t plus the phi. So let's guess that the results of this differential function, right, differential equation equal to this function x, where the a, omega and the phi are just constants. Right now we're not defining the a, omega and the phi yet, okay, so just say that it's just some constant here. Okay, then let's plug in this into this equation. So let's find the this derivative first, right? So we have, okay, just start from the first derivative, the first order derivative, dx by dt equal to, okay, now we need to find derivative of this one, right? So we have the a, which is constant, and derivative of the psi equal to cosine. So we have the cosine of the omega t and then plus phi. And then we need to find derivative of this argument, right? Derivative of this argument. Derivative of the omega t equal to the omega, and derivative of the phi equal to the 0, because the phi is constant. Then we can have that the dx by dt, right, equal to the omega a times the cosine omega t plus the phi. So if you remember, we know that velocity v, right, just equal to the dx by dt. So it means that in this case we can just say that the v equal to the dx by dt. Okay, so this is going to be the velocity of the mass. I said the object, right? The velocity of the object. Okay, the next thing is we need to find the second order differentiations. So we have the d square x by dt square equal to, okay, so now let's find derivative one more times. We have the omega and then times the a, okay, and derivative of the cosine equal to negative sine, so we have negative sine here, and then the omega t plus the phi, right? And then derivative of this argument of the cosine function equal to the omega, so just the same as the previous one. That's why we have the omega square here. Okay, and don't forget that derivative of the velocity, right, is just equal to the expression. So then that's why we can get the expression equal to this function. So this is going to be the acceleration of the object. Okay, the expression of the objects. Okay, now let's see. You may notice that this term, oops, sorry, no, this one, right, is equal to what? This one is just equal to this case. Okay, it's just equal to this case, a sine omega t plus the phi equal to the x. Okay, this is equal to the x. Therefore, you can see that we have the a equal to negative of the omega square and then times the x. Okay, and then times the x, which is the same form as this equation, right? I mean, if you move this to the left hand side, it's going to be the positive. Okay, it's going to be the positive here. So that's why you can get that this one is equal to the 0. Okay, so you can see if you compare this by this, right, it just have the same form. Okay, it just have the same form here. Then we can conclude that this omega square, okay, it must be equal to the k over m, because this is equal to the a already, right, and we have the same x here. So it means that this omega square must be equal to the k over m. Okay, and that's it, right? So now for the conclusions, we can say that, okay, these equations, okay, this equation, okay, is called the fundamental equations for the simple harmonic motion. So you can have this form. Okay, it's going to have this form. It means that if we have any motions, and then if we try to find equations of the motions of that particle or that object, and then if the equations of the motion has the same form as this one, it means that the particle or the object will move as the simple harmonic motion. So that's going to be the point. Okay, that's going to be the point. If we try to find equation of the motion of an object, and then if that equation just look exactly the same as this one or has the same form as this, right, it means that that object will move as the simple harmonic motion. So that's why this question just called the fundamental equation for the simple harmonic motion. Okay, and then what is the solution of this question, right? The solution of this question just equal to this one, okay, or just equal to our guess here, equal to this one, right? We call the omega, okay, we call this omega. Okay, the omega here equal to the square root the k over m. So now this omega is just called the angular frequency. Remember, we have used omega already in the circular motion, right? That's only one thing. And then in the rotational motion, right? But now that's omega, we just call it as the angular velocity, right? But now in this topic, for the oscillations, for the supersonic motion, the omega is called the angular frequency, not the angular velocity. Okay, but if we have the same unit as the angular velocity, so the unit is the radian per second. Okay, so we can define the omega in the same way as the angular velocity. So the angular frequency here equal to the 2 pi times the frequency f, right? And then equal to the 2 pi over the period t. So where the period t is the time for one oscillations. Okay, the time for one oscillation. For example, if okay, let's go back to the spring mass system here. So okay, let's see that if okay, now if the box just move up and down, okay, move up and down, right? So the time that the block just move up and down is called one period, okay, because it's the object just move in the one oscillation, right? Just move up and down is one oscillation. So the time for an oscillation is called the one period here. And now for the frequency f, right, is the number of the oscillations per unit second. So it means that in 1 second, how many oscillations that the object can cover. So that's called the period. Then again, right, we usually use the period, unit of the period, right, to be the second, and then unit of the frequency to be what? To be 1 over the second, right, or we just call it as the hertz, because the period and the frequency are the reciprocal to each other. So let me just write down here the f equal to the 1 and then over the period t. Oops. Yep. Okay, so we talk about this omega already, right? So now the amplitude, okay, and the phi. The A here is just called the maximum, it's called the amplitude, okay, it's called the amplitude. It's going to be the maximum displacement of the object from the equilibrium position. So if we just come back to this picture again, okay, so now you can see that no, it's quite difficult to see. Oh wait, okay, so let's say that, okay, this is this will be the maximum extension, right, and this will be the maximum compressions, okay, extension, compress, extended, and compress, right? Then at the midpoint between the maximum compressions and the maximum extension is going to be the equilibrium position, okay? So it means that the distance from this equilibrium position to the maximum compression is going to be equal to the amplitude. On the same way, the distance from the equilibrium position to the maximum compressions is going to be the amplitude as well. Okay, so that's called the amplitude, the maximum displacement from the equilibrium position of the spring, right? And then finally, the phi is the initial phase of the object, okay? It's going to depend on the initial conditions of the object. So just talk about it one later. Okay. Now then, let's consider the graph. Okay. So this graph is taken from survey's textbook. Okay, so this graph is taken from the survey's textbook. Okay, So now you can see that we have velocity of the object, right, to be equal to the v, and then times the omega a times the cosine omega t plus the phi. And then we have the acceleration of the object, right, to be equal to the a equal to negative omega square and then times the x. So one thing that we can get from the x and the a is that the phase difference between the position and the acceleration, right, must be equal to the 180 degree. Why? Because this one is positive and this one is negative. Okay, so if we look at the graph, you can see that, okay, if we draw the x, right, to be this curve, okay, so the horizontal axis is going to be the period, the time t, and then the vertical axis, right, is going to be the position. Okay, so now you can see that the time from one maximum to another maximum, right, it's just called the period of the oscillations. I mean, as I just mentioned already. And then the maximum displacement is just equal to the a, the amplitude of the oscillation, because this a is with the distance from the equilibrium position, right, when the x equal to the 0. Okay, so we said that at this position, okay, so we have the x equal to the 0, so it's called the equilibrium positions. Okay, then the maximum displacement is just equal to the a here, and that's it. Okay, so now you can see that from this graph, right, okay, the object just go up and down, up and down, up and down, etc. How about the acceleration, right? We said that the phase difference between the acceleration and the a just equal to the 180 degree. So if the a is going up, so if the acceleration is going up, it means that the a must just going down. Okay, so that's why we just flip the graph of the x, right, to have the graph of the a here. Okay, so this is what we just get. We have the maximum expression here, right? So let's talk about this one later. Okay, and then for the v, okay, so now for the v, the graph x is sine, the graph v is the cosine. It means that the phase difference between the graph x and the graph v, right, is just equal to the 90 degree, because sine and the cosine has the phase difference equal to the 90 degree. So that's why we have the graph just look like this one. Okay, so it means that we just need to shift the graph by 90 degree. Okay, so then what is the Vmax and the Amax, right? What is the Vmax and the Amax? You can guess from this graph that the Vmax, right, should be equal to what? Okay, so let's look at equation of the V. We know that the cosine omega t plus the phi, the maximum value is just equal to 1. Okay, then the Vmax should be equal to the amplitude, right, of the velocity, which is equal to the omega and then times the a. So that's called the maximum velocity of the oscillation, the omega times the a here. Okay, and now how about the Amax? Okay, how about the Amax? Again, then we can just look at the function of the expression a. Okay, this one. Then we know that the sine omega t plus the phi, right, the maximum value is equal to the 1. Then the maximum value of the expression must be equal to the omega square and then times the a. So I mean, right now we just ignore the negative sign, right, because we just want to take only the magnitudes of this one. So we have the omega square and then times the amplitude to be the maximum expressions. Okay, so now let's conclude this in this picture. Okay, let's conclude this one into the picture here. Okay, so now let's consider when the object is at the x equal to the positive a, okay, at the maximum amplitude here. You can see that when the object, right, is at the maximum amplitude at this position, okay, the velocity of the object must be equal to the 0. Why? If the velocity of the object is not equal to 0, it means that this object will just continue moving to the right hand side, right? But now we said that this is the maximum displacement, it means that the object will not moving to the right hand side anymore. So then at this point, the object will make the turn from right and then to the left. So the velocity of this point must be equal to the 0 corresponding to this portion of the graph. Okay, then we have that the v here must be equal to the 0. And then how about the accelerations? Okay, at this position, the spring will be extended at the most, right? At this position, the spring will be extended at the most from this equilibrium position, okay, from this equilibrium position. So let's say that the extension of the spring at this position just equal to the a, okay, just equal to the a. Then we can get that the extension of the spring, right, it just equal to the omega square and then times the a, which is the maximum value. But one thing that you need to be careful is that the spring try to pull the object back to in the left hand side, right? Because the spring try to pull the object go back to the equilibrium position. So it means that the direction of the spring force go to the left hand side, and it means that the direction of the acceleration must go to the left hand side as well. Okay. Now, so the block M, right, it just go faster and faster and faster because the direction of the force and then the acceleration are the same. So the block M will just go faster, and then after the block M just passing the equilibrium positions. At this position, the acceleration equal to the 0 because at this position, right, the spring will not be extended or compressed anymore. So that's why the extension or the compression equal to 0, and the acceleration must be equal to 0 as well. But then how about the velocity? Okay, how about the velocity, right? The velocity at this position when the x equal to 0 must be maximum value. Okay, it must be the maximum value. So then we can get that the velocity is equal to the omega and then times the a. But now I just want to put the plus and minus sign in this case. Okay, so the minus sign just means that the object just go to the left hand side, and the plus sign just means that the object just go to the right hand side. Remember, in one-dimensional motion, we said that go to the right is going to be the positive, and go to the left, velocity must be negative. So that's why I need to put the plus and minus sign here to say that the velocity must be positive or negative. To the positive, it means that the object go to the right, and for the negative here, it means that the object just go to the left hand side. Okay, so that's for the velocity. And then after the object, right, passing through this equilibrium position and then go to the left, you can see that the object will go slower and slower. Why? Because as the object just moving to the left hand side, so right now the spring try to pull it back to its equilibrium position. Okay, the spring try to pull it back to the equilibrium position, and then, right, the object will stop at this position. Okay, so it means that at this position the velocity again equal to 0, right? At this position the spring will have the maximum compressions. Okay, then it means that the acceleration must be maximum as well. So that's why we have the expression to be the plus omega square and then times the a. The plus side just means that the expression just go to the right hand side. Okay, so what I have explained, right, are described in this graph already. So you can see that. Okay, let me just explain one more time. So when the object, right, is at the maximum displacement or the amplitude, right, at this position, and it's moving to the left hand side, okay, so it's just moving to the left hand side here. So then after passing the equilibrium position, the speed must be maximum, right, equal to the negative omega times the a, because just moving to the left hand side, and then the acceleration equal to 0. And then, okay, after passing the equilibrium position, if we just slow down, okay, and then it will reach the 0 meter per second again at the x equal to negative a, right? So at this position, and in this position, the amplitude is going to be the maximum and positive, right? And then after that, the spring will just go back to the equilibrium position and then finally go to its original position again, right, into this one. And then later on it just go back and forth forever. Okay, so this will be the description of the simple harmonic motions. Now we need to find velocity of the object as function of the x. Okay, we just want to find the velocity of the object as function of the x. Let me put the box here first. Okay, so now we need to find the velocity of the object, right, as function of the x, the position of the object. How? Okay, so let me copy these equations. Okay, and then let me copy these equations. Okay, so we say that the sine square blah blah blah, right, the sine square blah blah plus the cosine square blah 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 equal to 1. Okay, the sine square plus cosine square equal to 1. So I mean this the trigonometric identity you have seen already. Now we can just write down the sine, right, in terms of the x and then over the a. In this case, we have the x square and then over the a square, okay, plus. So now we have the cosine square. Okay, so I'm gonna move the omega a to the left hand side. Then we have the v square and then over the omega square times the a square equal to 1. Okay, equal to 1. Okay, we just want to find the v as function of the x, right? So now let me just move the x square over a square to the left hand side. So we have that the v square and then over the omega square a square equal to the 1 minus the x square and then over the a square. Okay, so now let's just move the omega square a square to the right hand side of the equation. So then we get the v square equal to the omega square, and now it's going to be the a square minus the x square. Okay, then finally we can get that the velocity as function of the x, right, is going to be equal to, okay, we need to take the square root of this one, right? So then we have the omega square, we can just bring out from the square root, it's just equal to the omega, and then the square root of the a square, and then minus the x square. Okay, and let me just put the plus and minus sign here. Then again, plus and minus sign just represent direction of the object, right? Direction of the motion of the object. Okay, so this question is the link between the velocity and the position. Actually, we can check, right? We can check. Okay, so we can check that when the x equal to the 0, okay, when the x equal to 0, so you can see that we have the square root of the a square, right, just equal to the a. So that's why we can get that the v equal to the plus minus omega times the a, okay, the maximum speed at the equilibrium position. And now when the x equal to the plus or minus a, Okay, so when the x equal to the plus or minus a, we have the a square here, and now this a square just cancel out with this a square, which is equal to 0. So that's why we get the velocity equal to the 0 in this case. So the object is not moving when at the maximum compressions and at the maximum extensions of the spring. Okay. Now, how about the energy? Okay, how about the energy? We need to find the total mechanical energy of the system. Okay, remember when we talk about the total mechanical energy, it means that the kinetic energy plus the potential energy. Okay, so let me make this one to be red. Oops. Yeah, I need to. Okay, the total mechanical energy, the symbol is the E, right? Equal to the kinetic energy, the capital K, and then plus the potential energy, the U, okay, which is equal to. Okay, so now for the kinetic energy, right? For the kinetic energy, equation is the 1/2 m and the v square. The m is the mass of the object and the v is velocity of the object, and then plus the potential energy of the spring, okay, which is the 1/2 k and then x square. So this is equation of the total mechanical energy of the system. Okay, so don't forget that we talk about the system. Our system consists of the spring and the mass. So now this part just come from the object, which is the mass equal to the m, and this part just come from the spring with the spring constant equal to the k here. Okay. We can get more from this one, right? Because in this case, the total energy of the system is conserved. It means that there's no energy loss and no energy gained during the motion of the object. Then it means that the total energy of the system at any point must be equal to the total energy at x equal to 0, and then equal to the total energy at the x equal to a. I mean the plus minus a here. Okay, then again we can say that the E here, right, must be equal to, okay, if we look at x equal to 0, right, we have only the kinetic energy, so it's just the 1/2 m and the v square. So this v, we have the omega square times the a square, right? Okay, so this one is at the x equal to the 0, and then also it must be equal to, okay, if we look at the x equal to the plus and then minus a. So now for these two positions, we don't have the velocity of the object. It means that the kinetic energy of the object must be equal to 0 as well. But we have, okay, the maximum extensions and the maximum accelerations. It means that at these two positions, we will have the maximum potential energy of the spring, right? Because the spring will have the maximum extensions and the maximum compressions. So the spring will have the maximum elastic potential energy, which is equal to the 1/2 k and then times the x squared, right? In this case, it must be equal to the a squared. Okay, so this and the x equal to the plus minus a. Actually, if you compare these two, right, you can see that this k must be equal to the m times the omega square. Why? Okay, why? Just come from this equation, the omega equal to the square root k over m. Okay, just come from this equation, the omega equal to the square root of the k and then over m, right? Then if we square the both side of the equations, we have the omega square equal to the k and then over m. Or we can just get that the k equal to the m and then times the omega square, and that's it. Okay, so it means that this k equal to the m omega square. So these two equations are the same, right? And actually we can just use this relationship to plug into this one as well, so no problem at all. Okay, so now for the conclusions, we can get that the E, the total mechanical energy, equal to the 1/2 Ka square. Okay, so let me just write this. Let me just only write this one down, and then equal to the 1/2 m the v square plus the 1/2 k and the x square, and that's it. Oops. Okay, so now how about a graph? Okay, how about a graph? If we just want to make the plot between, let's say, the position as the x-axis and then the energy to be the vertical axis. Okay, so let's define here that, okay, let me check. Okay, so let's say that at this position, right, x equal to the plus a, and here x equal to negative a, right, and 0. So these two just be the this be the maximum extension of the spring, and this be the maximum compression of the spring, right? Then the graph of the total mechanical energy should be just this line. Okay, so this equal to the E, because the E must be constant, right? So that's why it's just equal to this one. Okay, so now for the graph of the elastic potential energy, the 1/2 kx square, right? You can see that it's just the parabolic function. Okay, so when at the x equal to 0, energy equal to 0. When at the x equal to the a, right, the energy we have the maximum, then the graph just look like this. Okay, so this can be the graph of the I use symbol as the u, right, the graph of the u here. Okay, and then finally for the kinetic energy, right, for this one, you can see that when at the x equal to the plus or minus a, right, the speed equal to 0, so these 2 points, and then at the x equal to the 0, the speed is maximum. Then again, right, the graph just look like this. Okay, so this is the graph of the kinetic energy. So one thing that you can get from this one is that the k plus the u, right, must be equal to the E. Okay, so maybe we can just consider this. This length, oops, wait, this length. Okay, so if we look at any position x here, okay, so this length and then plus this length, so I'm gonna make thinner and maybe dash, yeah. Okay, so the blue one plus the red one must be equal to the black one. And maybe here. Okay, so this length plus this length must be equal to this length, and that's it. Okay.